Another well-known dynamic programming algorithm is Floyd's algorithm for computing the shortest paths between every pair of nodes in a given graph. This is very similar to Warshall's algorithm, and in fact, if you haven't reviewed the lesson on Warshall's algorithm, I strongly suggest that you go back and look at Warshall's algorithm before going through this lesson on Floyd's algorithm. So the Allpairs shortest path problem is given a graph where we have a weight matrix, that is the length of each edge or the distance or the cost of each edge in the graph is given to us in a matrix form. For example, if there are n nodes in the graph, then this matrix will be an n by n matrix. And what the algorithm computes is a distance matrix, that is, for every pair of nodes it gives us the length of the shortest path between those two nodes. And of course the algorithm can be extended slightly to obtain a version which will actually return the path, not just give the distance. But the regular version of Floyd's algorithm gives us the length of the shortest path for every pair of nodes. Just as in the case of Warshall's algorithm, we do not apply a brute force technique to just compute this separately for every pair of nodes. Instead, we apply a technique very similar to Warshall's algorithm to iteratively go through all the paths to find all pairs of shortest paths in the graph. So if we first ask the question, is there an edge between the two nodes? If there is an edge, it's quite likely that that is the shortest path, but although there is no such guarantee. There may be paths going through other nodes which are shorter than the direct edge, because the weight of that edge may be higher. Next, if that is not the case, we ask, is there a shortest path going through only node number 1? Right? And then we ask, is there a shortest path going through only nodes 1 and 2? Then going through 1, 2 and 3 and so on. The same technique that we used in Warshall's algorithm is also used in Floyd's algorithm. So the idea of Floyd's algorithm is, let's say there is a node I, right, and a node j. Now we are considering a particular node k. Then the shortest path from I to j may be a path like this. We don't draw a straight line because it's to indicate that it may be going through a number of other nodes that we are not representing in this picture. Now those other nodes are all the nodes from 1 to k minus 1, or it may actually go through the node numbered k. In this case, there will be some shortest path from I to k and another shortest path from k to j. Why should these be shortest paths? Because otherwise the principle of optimality will not apply. The principle of optimality in dynamic programming says, if the shortest path from I to j in fact goes through the node k, then the path from I to k must also be a shortest path from I to k, and the path from k to j must also be optimal. That is, that must also be the shortest path from k to j. So there are two possibilities when you are considering node k. Either the shortest path from I to j does not go through node k at all. It only goes through nodes 1 to k minus 1, or it goes through node k. So we do this repeatedly from k1 to n, and in the end we will get the shortest path from I to j that can go through any node in the graph. This sequence of decisions that we make as we increase k gives us the dynamic programming solution to this particular problem. So if this distance, the distance of this path, is represented as d superscript k minus 1 I comma j, this one would be d superscript k minus 1 I comma k, and this would be d superscript k minus 1 k comma j. So from this we can conclude that if d k minus 1 I comma j is less than the sum of the other two, then that will be the shortest path. If the sum of these two is shorter than the distance in the other path, then that will be the shortest path. So what we do is we take the minimum of the two, the minimum of d I to k plus d k to j. Both of these are superscript k minus 1. Right? So we take the minimum of these to be the shortest path. Right? So either it is the direct path from I to j or the one going through k. And what will that give us? That gives us d superscript k of I to j. Because now it may go through k or may not go through k. By taking the minimum, we will get the distance. This is essentially the formula that is applied, or the recurrence that is applied to obtain the Floyd's algorithm. Let's look at an example first. So we have 4 cities here: Pune, Mumbai, Bangalore and Mysore, and the approximate distances are shown here. In the actual geographical map, all roads are two-way. Just to make things interesting, we have made all roads one-way. For example, you can go from Mumbai to Pune for 200 kilometers, but there is no way to go back from Pune to Mumbai. All of these roads are one-way. So if we write the initial weight matrix, right, which is usually denoted by W, that would be a 4 by 4 matrix, 1, 2, 3, 4, or Pune, Mumbai, Bangalore and Mysore. The distances are, we always make the diagonals 0 because the distance from a place to itself is 0. And then there is only from 1, there is only an edge to 3. All others are infinity. So this is infinity, 800 and infinity. Similarly from 2 there is an edge to 1, 200, and then there is no edge to 3 or 4. So those will be infinities. From 3 we have an edge to 4, all others, and also to 2. So this is infinity, 980 and 150, and then from 4 we only have an edge to 1, 750, and the others will be infinity. So this is the initial distance matrix or weight matrix. From this we are going to apply Floyd's algorithm and obtain the shortest paths from any node to any node in this 4-node graph. And in doing so, we will see how the principle of optimality and the taking of that minimum will give us shorter paths as we iterate through Floyd's algorithm. The structure of Floyd's algorithm is exactly the same as that of Warshall's algorithm. So we are given the weight matrix, an n by n matrix. We take that to be the initial distance matrix. Unlike in the case of Warshall's algorithm, since we are only dealing with distances, we don't need to remember the previous version, so we overwrite the same D matrix for all the different values of k. So there are the 3 nested loops for k1 to n, for i1 to n, and for j1 to n, and we rewrite, we compute the new value of the distance I comma j to be the minimum of what was already there, or the sum of I to k and k to j, and we do that repeatedly, and in the end we return the matrix D. So let's see how it works in our example. So here is the graph again. So the initial value of the D matrix will be what we had just written there, 4 zeros along the diagonal, and infinity, 800, infinity. This will be 200, and the rest are not there. This will be 980, and then 150, 750, and the rest are not there. So now what happens when we compute the next value of D? So now we have to consider all the paths that can go through node 1, right? So the diagonals will remain zeros always, right? So the only changes will be, these will all remain the same. Let me write that and then I will show you how the changes occur. 980, 150, 750, and then infinity, right? The other two will change. Why will they change? Right? So the new value that we obtain here will be 1000, and the new value that we obtain here will be 1550. So in essence, this is D superscript 1. That is, we are now looking at paths going through 1. So from 2 to 3, right? There was no path earlier, but if you can go through 1, now you have a path, right, whose value is 1000. So that's how we now got a path. So this infinity changed to 1000. 4 to 3 there was no path, but now you can go through 1 to get to 3. So 4 to 3 is 750 plus 800, which is 1550. So those two new paths were added. The new paths were 2 to 3 and 4 to 3. They got added when we considered paths going through node 1, right? So the next value will be when we do the next iteration. So we are now allowed to go through nodes 1 and 2, right? And the changes will be, here you will get 1180, and let me see, that will be the only new value that we will get. So you will get a path from 3 to 1. Now 3 to 1, there was no path before, but now you can loop through nodes 2 and 1, right, and get to go through node 2 and get to node 1. So 3 to 1 is 980 plus 200, 1180. That was this infinity before. So we get a new value for that. Continuing along, right, if you write the next iteration, which is you can go through nodes 1, 2 and 3, but not node 4, then the new values that you will get are, you will get 1780 here, and then 950, and then 1150, lots of new values, and then 2530. So the paths that we are getting at this particular iteration are, this is 1 to 2, right, 1 to 2, and then this one is 1 to 4, and then this is 2 to 4, and then this one is 4 to 2. So why do we get these paths? Because if you consider 1 to 2, there is no path from 1 to 2 earlier, but now that we can go through node 3, we can do 1, 3, 2. Similarly, 1 to 4 via node 3, we can go to node 4. Similarly, 2 to 4 you can do via 2, 1, 3, 4, and then 4 to 2 we can do 4, 1, 3, 2. So that's the longest path we have found. 4 to 1, 1 to 3, 3 to 2. So these are the new paths that get added. So till now we have added a number of new paths, right? In the next iteration, when we include the values will change. In fact, at this point itself, we don't have any infinities, right? So we have this as 0, this is 800, this is 200, then you have a 0, then you have 1000, then this one is 1180, 980, 1980, and then 150, 750, oh sorry, this is a 0, and then 1550 and 0. So there are no more infinity. That is, we have already found a shortest path from every node to every node. But in the final iteration, d superscript 4, some of those values will change. What will happen is you will get new values for the path 3 to 1. So 3 to 1 will get reduced to 900 from 1180. Why does that happen? Because if we are not allowed to go through node 4, the path we had found from 3 to 1 was 3 to 1, and the cost of that was 3 to 2 980 plus 200 1180, which is what we had here. Now that you are allowed to go through node 4, you can do 3 4 1, right? And the cost of that is 4 1 is 150 plus 750 is just 900. This is a shorter path. So that shorter path replaces an existing path, and we got the globally shortest path between node 3 and node 1. So this is how dynamic programming works in the case of Floyd's algorithm, to give us the most optimal solution for the shortest paths between every pair of nodes in a given graph. How long does it take to do this? The analysis is the same as what we saw in the case of Warshall's algorithm. The number of edges don't matter, the actual values of distances don't matter. You have 3 for loops from 1 to n. So this is theta n cube, where n is the number of nodes in the graph. So that is how Floyd's algorithm works, to give us the shortest paths for every pair of nodes in a graph by applying the techniques of dynamic programming.